My name is Ted Malaska. I work for Cloudera. I'm a principal solutions architect. I've been doing Hadoop and distributed technologies for over 6 years. I've contributed to a bunch of open source projects. I wrote that book, which, by the way, after this session, as soon as I can get back to the booth, which is probably like 10 minutes after the session, right? We're going to be giving out 20 free copies, I think, or 25 free copies. So if you want one, just follow me to the expo, to the O'Reilly booth. I've gotten the pleasure of working for over 70 companies. I think it's somewhere around 100 or so companies around the world, and I've seen a lot. And I'm a big Marvel fan. I really enjoyed the Civil War that came out like a week or two ago, and I'm a runner. So, all right. So what are we going to talk about? So we're going to be talking about, the journey we take in learning code. We're going to be talking about distributed programming. We're going to be talking about, Spark. We're going to be talking about managing parallelism. I have to stay here, otherwise you can't hear me. And we're going to be talking about, considerations we need to have with regards to memory. So the rule of thumb here is raise your hand whenever you want, as often as you want. If you have a question, let me know, and we'll dig into it. The content is mostly entry level, but if you want to dig deeper, we can definitely do that. All right. Okay. So there's lots of things we have to do when we're learning a new code base or we're learning a new paradigm. Learning the code itself is, relatively, there's a difficulty to it, but it's easy compared to the mindset we have to have, and what are we trying to solve, and where are all the underlying costs. So an example I can give here is my own journey with software, right? So I started coding when I was 8 years old. And I remember the very first concept that I had to grasp was this idea of variables, right? And when I'm teaching my kids, it's like, oh, the value for this will change. And it takes them a little while to figure that out, right? So X can be 1, but then I can set 2, and then it changes, right? And then the next big thing you have to learn is flow control, right? Your if statements, your whiles, and then you have these monolithic applications that then you understand that you can make functions and split things up and use repeatable code. And then the big one is object-oriented programming, right? When I was young, that was a big thing. It was like, oh, wow, Java came out, and it's object-oriented, and it's a whole new world. And then the next one after that, I think, for me at least, was threads, right? Mastering threads, mastering when they should intersect, when to use synchronized blocks, when not to, how to maximize throughput with your CPU and stuff like that. And I think the last one is the one we're going to talk about today, and that's distribution, right? So it's like an extension of threads, at least in my concept. And I think very much so in that when threads need to communicate, there's a cost. When in distributed programming, when your different distributed tasks need to communicate, it's even more costly, right? Now, we're going to be using Spark as the framework to talk about distributed programming, but anything we talk about here will apply to MapReduce, it'll apply to Flink, it'll apply to several of the streaming frameworks that are out there today. We're going to use Spark just because Spark is the juggernaut right now. It is the most contributed open source project in history. Right now it's used by a lot of people. All right, so let's break down our distributed model, our distributed application in terms of Spark, right? And in Spark, there's 3 types of things out there, or executables out there. There's this thing called a driver, and there's only one of them per Spark application. And then there's n number of executors. So if you have a 100-node cluster, you could have 400 executors or more, depending upon how many resources you have and stuff like that. And then there's this shuffle service, right? And I'm pulling that out as a separate box. So the driver, we'll get into it a little bit when we start looking at the code, but consider the driver to be like the brain, like the orchestrator. If you're familiar with query engines, this is where your query plan would be generated and stuff like that. And then the executors, think of them as the workers, right? And the shuffle service, we'll get to that in a minute. So some of the paradigms we need to think about is what ways do these different services communicate, right? So one is this concept called a broadcast. A broadcast is when you have information, normally small enough information, and when I say small, normally underneath a gigabyte worth of data, normally underneath 1 million records if you're doing like a broadcast join. And a broadcast is information that you have in your driver, your controller logic, and that you want to put that information on every single executor, right? And you can imagine there's a certain cost to this. You have to transmit that data to all the executors. So that's the first method, right? Then there's this idea of the take. So this is information that the executors have that you want to bring back to your control flow, like your driver, to maybe print it out, to maybe write it to a file or something like that. The problem with this one, as opposed to the other one is you're taking a small set of data and you're broadcasting it out. The problem with this one is you could have hundreds or thousands of executors, and each hundreds of thousands of executors could have tons of data, and you're just one driver, right? So if you take too much data, you're going to potentially run out of memory. It's going to take forever to grab all that data. So taking is way more expensive and doesn't scale. So we need to be very cognizant of that and very respectful of that. And I'll show you when we get to the code what is a take and how to properly use a take. The next thing is this concept of a DAG. Does anybody know what a DAG is? Raise your hand if you know what a DAG is. All right. I'm going to show you a graph in the future. Before I show you the graph, know that when I heard of a DAG engine, I was like, oh my God, a DAG engine. That sounds so cool. It sounds like a jet fighter. And then you'll see very soon here that I was hugely disappointed. But yes, DAGs are very cool. DAGs, and I'll show you the picture in a minute, but DAGs, if you can think about it, are just instructions. They're like, what should I do and what order should I do them and stuff like that. They get transmitted from the driver to the executor, so the executors know what they want to do. Now, since the DAG plan is very relatively small compared to everything we've talked about so far, this is a very inexpensive operation, right? So it's very inexpensive to send control flow logic to our executors. And the last one is this concept called a shuffle. If you've been around me a lot, shuffle is essentially my enemy. I want to stay away from shuffle as most as possible. But it is required in a lot of situations. A shuffle is something like if you're going to do a join, or you're going to do a group by, or you're going to do a reduce. So if you can imagine if you're the relational world, if you have two very large tables and you want to do a join, you need to partition that data, and you need to order that data so that the two sides can find their matches, right? So in a distributed system, a shuffle will look something like this, right? You'll have a map side, which will write out to a whole bunch of temp locations, and these temp locations will be broken up into partitions. So here we have each mapper writing to 4 partitions, right? And then we have a reduce side, which is each reading their partition from each mapper, right? So you can tell from the magnitude of lines that this can get really hairy, right? You don't actually have to think about this. This happens magically behind the scenes. But as you add more mappers and as you add more reducers, the number of boxes in the middle is the product of those two numbers, right? So if you have 100 mappers and you have 100 reducers, you have 10,000 intermediate files you have to deal with, and they all have to travel over the network. They all have to be serialized. If you're lucky and they fit in memory, they don't have to be spilled to disk, but you might not be that lucky. So we'll talk about this a little bit more as we go on, but shuffle is the most expensive of all the operations we've talked about so far, except for like a really bad take. So in general, if we do things right, more nodes will mean that everything will go faster. Exchanging data between all the services we talked about is extremely expensive. And we also need to understand, I'm going to show you a DAG in a second, that everything is going to be lockstep. we have to do one step before we do the next step. Any questions on any of those concepts? No questions. All right. If you're falling asleep, please let me know with a good snore. OK, so what makes Spark Spark? So when I think about Spark, I think about these four things. There's RDDs, and they also can be called data frames. There's DAGs. There's this thing called Flume Java. And then there's this concept of long-lived applications, right? So I'm going to walk through each one of those. So RDDs, resilient distributed data sets. So what are they? They're this concept of immutable data that's distributed across the cluster, primed to be executed on, right? Some very important concepts here. It's immutable. You cannot change it. And we'll see in a minute when we look at the DAG, immutable is important because in a distributed system, we can have failure, right? We can lose nodes, we can lose drives, we can lose switches, but our job should continue, right? And it should be able to recover. And immutability is a very important part to being successful there. The next thing that you can do is RDDs by themselves don't have any type of schema related to them. A big advancement that came in Spark a while back is this concept of the data frame. And a data frame is nothing more than your data that has a schema, right? And it has some structure. And that means different people can, it's easier for other people to be able to read them, but also depending upon what you're doing with it, Spark can then take advantage of your data structures and optimize it even more further for operations like Spark SQL, right? So RDDs in themselves isn't that amazing, but what they do allow us to do is they allow us to do a DAG. So if any of you have done MapReduce, how many people did MapReduce? OK, so in MapReduce itself did not have a DAG, right? If you wanted to make a DAG, you either wrote a Hive query or a pig statement, and then it generated a DAG for you, or you wrote an Uzi script that would chain a lot of MapReduce jobs together. So all a DAG is all the steps that need to happen from you to get to point A to point B, right? So if you said, I want to join these two tables, and I want to do a group by at the end, and then do some aggregation, that could be a multi-step operation in a DAG. The big thing that Spark allowed us to do was this DAG now lives in the engine, right? Before, the engine was independent of the DAG and was executed throughout the DAG. But now that we have this engine that is cognizant of the DAG, it can keep things in memory, so it never has to touch disk in between positions in the DAG. And this is really helpful for things like iteration, things like machine learning, and especially if you have data sets that aren't huge, right? So, well, huge relative to your cluster, because you can fit them into memory. So remember when I said I was unimpressed with a DAG? So this is a DAG. It's a directed asynchronous graph, a cyclical graph. So what's the important thing here? The only important thing is this is a whole bunch of dots connected by lines that don't loop back. That's pretty much it. It's a one-way map of flow control, right? And the way it is you have a source, you have RDDs, and you have actions, which are the black dots. We'll talk about those in a minute in code. And then you have transformations, right? And we're going to talk about transformations and actions in a little bit. Actually, we're going to talk about them right now. So an action is something when you ask a question, right? So you say, well, how many records are in this RDD? Or a take is like, I would like to grab all the data from this RDD and bring it back to my driver. And a for each is saying, I would like to perform an action on every single record in that RDD. Because these are actions, they actually start the execution. Now, transformations, things like reduce by, group by, join by, map, and I didn't put it on here, but even Spark SQL, these are transformations, right? Transformations don't actually execute until you ask a question. What they do is they actually just build the DAG. So if you run in Spark and you actually write a map, nothing actually happens at that point. If you say reduce, nothing actually happens at that point. But then when you say count, then it does a whole bunch of work. Okay? So why is this all important? Like I talked to you before, let's say we had a failure while we're computing, this step in our DAG, right? If we have this failure, Spark will say, hey, something went wrong. I'm going to re-grab the previous step, and I'm going to recompute where I failed, and then I can continue to go all the way to the end, right? So, okay, so at this point we talked about two things. One is how the different execution parts of Spark interact, and some things we have to think about in terms of performance, and then the concept of a DAG. I'm trying to build on different concepts, and now we're going to get to code, right? So hopefully it'll make a little bit more sense when you can look at the code. So there was this concept called Flume Java, which was announced to the public at a Google I/O. I forget the exact year. I want to say it's like 2008 or something. But the concept was really simple. It was, I don't want to write Uzi anymore. I don't want to go to like a BPM engine. I don't want to go to a scheduler. I don't want to have to write SQL. I want to write code, just regular code, that'll run in my local machine, but then when I put it on a cluster, it'll run distributedly. And the same code can run in both models. It can run in a single-threaded way in my IDE so I can debug it. But then if I put it in a cluster, it can distribute the workload on the cluster. This was a very cool idea, right? And I'm going to try my best to show you why this is very interesting. So this is an example of word count in Spark. So if you're unfamiliar with word count is very important to things like search algorithms and stuff like that. And it's because the words that are most said are the most irrelevant, right? So the, and, or are the most irrelevant in terms of search indexing. So this was one of the big MapReduce use cases back in the day. And so this was a good example for Spark. So what's really going on here, right? So in line 1 and line 2, we're just setting up what's called a Spark context. This is kind of like our central place where we're going to be doing driver functionality. And then what we're doing in line 3 is we're saying, Spark context, can you read this file for me, right? So that goes into this variable called lines, right? For our purposes, that's an RDD. That lines is an RDD. Nothing actually happens at line 3. No work actually happens. All we do is we add to the DAG. The next thing we do is this thing called a flat map. And a flat map may sound intimidating to somebody who's not familiar with map and reduce and stuff like that. It essentially says go over every single value in this RDD, or if you think about just Java in a list, and split that value into possibly more values. So when we read a text file, we read a line at a time. So what's happening here is with our flat map, we're taking our variable, we're splitting it, we're doing a string split based on space. So now we're getting every single word. So every single line came in, but we possibly could have n number of words for that line coming out. And that gives us the variable words, right? And that's just an RDD. But from your perspective, it's just a list, right? It's just another list. Then we take word and we do a map on it. And a map is a concept of take every record and return a mutated record, right? So in this concept, we're taking every word and we're returning it as word and the number 1, right? So there's this concept called a tuple, which is just a quick way of making a combined object. And that goes into this thing called pairs, okay? And then the next thing is this thing called reduce by. And reduce by key, what it says is the key is the first thing in a tuple, and the next thing in the tuple is the number, right? So this fancy little syntax down here, I'll show you the Java implementation in a minute, is essentially saying take the number from, if you find two people with the same word, so you find cat and you find cat, and this guy has a 1 and this guy has a 1, take the two numbers and add them together and return cat2, right? And then if you have cat2 and you find another cat1, combine those together to make a cat3. And the result of a reduce by key is you're only ever going to have one cat, and then you're going to have the aggregate value for whatever on the right side. Okay, so that comes out with word counts. So that's in line 6. Now up to this point, nothing has actually happened, right? So in line 7, we say take. We're saying take the first 100 records, and that's going to return a local collection. And then in that local collection in line 8, we actually print it out. Now I know that's a lot, and if you're not a Scala developer, some of this might be a little intimidating. But let me start breaking it up. Of that entire code base, the items in green are items that could be distributed across the cluster. Everything that is in white actually executes on the driver. Okay? The green stuff, if you are running on your local machine, will run in the same JVM that everything else runs in, that your driver runs in, right? But if you're on a cluster, what will happen is those green bits of code will actually get distributed across the cluster and execute in parallel, okay? And more so, even if you're running on your own laptop, you can set the number of threads that will happen on your own laptop, and those green items would run in different threads. Does that make any, that's cool? All right. You got to help me. Otherwise, I think you're either falling asleep or you're just, or I'm giving you too much, or I'm boring you to death. So the next thing is I wanted to call out is everything in blue is a transformation. So everything in blue is just making the DAG for us. It doesn't actually do anything. The first time we actually do an action is the red code, right? And that's where we're bringing stuff back to the driver. And then green is totally just local code, has nothing to do with Spark. That's a local collection, that's a local for each, and that's a local print, right? Now, for the people in the room that like Java, this is what it looks like in Java. And this is why I don't use Java, because it's bulky. But we can definitely walk through this, right? Actually, it's the exact same thing. So we're doing a flat map on the lines, and you can see we're doing a string split, and that gives us an array. And line 8, we return that array of cells that goes into a RDD. And then in line 11, we're doing our pair, and you can see in here a tuple is a little bit more, verbose to define it. My tuple is a string and an integer, and I'm returning a whole bunch of strings and integers. My reduce by key, now this is much more verbose than the Scala version. You can see that in line 20, I'm taking the int value from the right side and I'm adding it to the int value of the left side, right? It is a lot more explanative, or like it's easier to really understand what's going on if you're unfamiliar with Scala, but you can understand once you get used to this syntax, it's a lot nicer. But anyways, and then we do the word count, and notice that on the take in line 23, it's a list now. It's not an RDD. It was always an RDD before, but now it's a list. And then line 24 is just a for loop, and we're doing system.println. Any questions on that? No, does that make sense? Okay, yes. Yes, if you use Java 8, that would be tighter. I did this presentation back when that just came out. I haven't rewritten that, so it would get a little bit better. It wouldn't fix everything, but it would get a lot better. I could read it. Yeah. So what he's saying is, why didn't I use the Lambda function? So in Java 8, they have new Lambda functions, which is going to bring the Java code closer to this side. Right? So it's going to look more like this. So if you're an anti-Scala person, don't worry, Java will turn into Scala eventually. The reality is it's so much easier to read once you get used to it, and it's so much less typing. And there's no more semicolons. I mean, that in itself wins. But okay, so again, everything in green gets sent across the cluster and executed. It's a little bit easier to comprehend it here. We're making objects, and those objects are getting sent across the cluster and then getting invoked on the executors, right? You don't really see that magic here, because it's kind of happening for you, right? These Lambda functions are kind of happening for you. But when you look at the Java code, you can see these are explicit objects with functions that are getting sent over the wire. They're getting serialized and then unserialized on the other side. So back to the same concept, this is all the transformation code. The red is the action code, and the green is it's just local execution, okay? All right. So now you can also do that in Python, but I'm not a Python guy. The Python will look very similar to the Java. All right, so let me quickly go over what I meant by long-lived applications, unless anybody had questions on that previous one. The big key there, let me just say one more thing. The big key there is if you use Java or you use Scala, it doesn't matter. You can run this on your local machine and you can debug it. You can step through it with the debugger, right? That's really powerful. And then you can take that same code and put it on the cluster, and then it's distributed, right? You can even run it on your local cluster by pulling data from your distributed system. It'll run real slow, but you could still do that. It's very powerful as opposed to what MapReduce was before. So, okay, so long-lived applications. So back in the day when we talked about the DAG is outside the execution engine, our world looked like this. We had an input, we have mappers, then we had a shuffle process, then we had reducers, then we had output. But that would only do maybe one join or one group by or something like that. So eventually we had to chain everything together, right? So we had this big monolithic thing that we had with Uzi or Hive or something like that. And then from the visualization of pane, everything in red required interaction with disk, right? And everything with yellow required spinning up and spinning down containers across the cluster, right? So you can imagine yellow and red are painful, right? So what Spark gave us was this. If I can go to the next page. What Spark gave us was this. We only have to spin up yarn containers once for the entire workflow. And if we organize the memory correctly, and we have a big enough cluster, we don't have to hit disk throughout the entire process, right? And then we're only really hitting disk at the very end. So you can see that this is way better than this, right? So the next question is, why can't I do this, right? And so this is where Spark Streaming comes in, and this is where Spark SQL can be used as a service that's reused over and over and over. And what this is saying is, leave the containers up, leave the memory available, and we can continue to use those executors without spinning down and spinning them up again. So in the mode of Spark Streaming, we can do iterations like every half a second and be able to do real accurate, real powerful streaming on a stream of data. The other big thing that happened since I made this presentation is there is an advancement known as dynamic allocation. And what dynamic allocation allows you to do is when your Spark application needs to do more work, and more work than the resources you originally gave it, it can grow dynamically. And when your Spark application has less work, it can shrink dynamically. And this is really important because there's this concept in Spark called like Spark Shell, or people are using these notebooks to type in Spark code. And what happens with this, at least what has happened with this in the past, is people will say, well, I want to take 10% of the cluster for my code, and I just want to start writing code that executes on the cluster. And this sounds really good in a sales presentation, but what happens is that person takes 10% of the cluster and then goes to lunch. And 10% of the cluster is still controlled by this person while he's eating a ham sandwich. And no one can use those resources. What dynamic allocation allows is when that person is inactive for a certain period of time, it will return those resources back to the pool until that person comes back to lunch and starts working again. So it's kind of pretty cool. Any questions on resource allocation? All right. Wow. Okay. I'm hopefully not boring everybody. Okay. So managing parallelism. This is the important thing, right? So up until this point, we've been talking about, you're writing and you're writing this distributed application, and it's magic with memory, and you don't have to hit the disk anymore. but does this solve the world's problems? Now, the optimal situation is this, right? If you wrote this code on a single machine, it would take, this long. But if you were able to run it on 6 machines, it would take 6 times less the execution time. And this is the hope. The reality is there is cost at the start and stop of those. So if you fragment it too small, that cost starts to add up, right? So that's one component of it. So if you're using too little parallelism, it's wasteful. If you're using too much, it's wasteful. And we kind of talked about fixed allocation versus dynamic allocation. Those will help grow to the right sizes. These are some parameters. Oh, why don't I go through it? So fixed allocation is the concept of you essentially say, how many cores do I want? How many executors do I want? How much memory do I want, right? And what the system will look like is you'll have these executors, and then you'll have work that will funnel into those cores. And those cores will pick up work as needed. The extra benefit of dynamic allocation is it would spin up another executor and take some of that work to that next executor. The next big problem with parallelism is this thing called skew. Has anybody ever experienced skew? No one. Wow. Okay. So skew is when you run a distributed program and it doesn't really get faster. And then you buy more nodes and then it doesn't really get faster. And then you go yell at your hardware vendor or your software vendor and say, why isn't my job getting faster? And then they look at your cluster and they realize that everything is running on a single core, right? And so this happens a lot with concepts like joining. And it's most common when you join 2 tables where one of the possible values is null for the join. And let's say 80% of the values have null. And there's a null key and there's a null key over here. And what this will do is when you do things like shuffle, it does partitioning based on the key. But if 80% of all the keys are null, then 80% of all the data is going to go to one core. Right? Does that make sense? So that's a bad thing, right? That's something very different than if you were just writing normal Java. Now you have to conceptualize, well, how do I split my workload across all my executors? So if you ever see during one step in your DAG, one task taking longer than, one core taking longer than all your other cores, then you have skew. Now I'm going to tell you there is no reason why you should ever have skew. Skew is not a mathematical given, right? There's always a way to fix skew. So a really quick way to fix skew, if I could show you real quick. So this is a simple data set that's skewed where 50% goes in one core and then 25% goes into another core. There's this little magic function that all parallel systems pretty much use as their basic partitioning logic. And it's the concept of doing a hash mod. How many people here are familiar with hash mod? Just curious. Okay, a couple. So how many people are familiar with hash, the hash function? All right, good. So the hash function creates like this random variable that's not random because if you put the same value again and you say hash, you get the same random variable again, right? So it's a repeatable random variable. And mod is a fancy word for remainder. In America, they just teach us it's a remainder. So if you say something mod by 2, so if you divided something by 2, your remainder can either be 0 or 1, right? If you mod by 3, your remainder can be either 0, 1, or 2. So doing a hash and then a mod is how these distributed programs will split your keys among all your partitions. So what you can do if you wanted to, you can add what's called a salt. And if you add a salt, you can see if you add a 2-layer salt, our distribution gets a lot better. If we add eight types of salt, we can distribute fully again, even though our data set was skewed. So a salt is just exactly what it is. It's putting a little bit of dirt in our key, right? So an example, if you're doing stock trades, Apple gets traded more than almost all of the stocks on the stock exchange, right? And you're doing a reduce by key, and you don't want Apple to go to just one core, right? What you could do is you could randomly say to every Apple transaction, your key is going to be Apple 1 and Apple 2. And at the very end, after you get the aggregation of Apple 1 and Apple 2, then you just add the two aggregations together, right? So you can use multiple cores then to process Apple. Does that make sense? All right, so that's the concept called salting. The other big thing that's out there that sucks is this concept called Cartesian joins. Has anybody ever done a Cartesian join? Yeah? Has anybody, is that ever a good thing? Or is it? So, okay, so with Cartesian joins suck. They suck terribly. And what essentially it is, if you're not familiar with it, is when you join two tables that have a many-to-many relationship, and let's say for key A, there is 1,000 items in this table, and for key A in this table, we have 1,000 items, right? And if you did a join to this, you would end up with 1,000,000 items, right? So your data set now becomes 1,000 times bigger, right? And this can only get worse and worse if you have more keys, like if you had 1,000,000 and 1,000,000, right? And at some point, this doesn't work because distributed systems scale linearly, and this scales exponentially, right? This is not a good situation. But it's totally solvable. I've worked at some places where I can use nested structures. Does anybody know what a nested structure is? All right, so one person does. So a nested structure, go look it up when you go home. I'm not going to go into it terribly here. But what you can do is you can actually have a cell in a table, and that cell has rows, right? So you can imagine if you were joining two tables, if you had a one-to-many relationship, you would have, let's say, Bob, and Bob bought 3 cats, right? If you would join them together, you're going to see Bob, 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 cat A, cat B, cat C. And you're going to see 3 lines, and Bob's going to be repeated 3 times. If you made cat a nested field, you would only have Bob once, and Bob, then you would have in cats 3 whole fields. This is this concept of nested fields. It started to get popular with Hive and Hadoop because joins became very expensive at scale. So if you could use nested types, those joins would already be done for you, right? So with a Cartesian join, what you can do is if you had 3 Bobs and 3 cats, instead of producing 9 rows, you can have 1 row with 3 Bobs and 3 cats. And then you can do the Cartesian algorithms that you're trying to do, like aggregation or something like that, in memory. And you don't have to write it out. You don't have to express it in memory. You don't have to express it on disk. Does that make sense? All right. I didn't mean to go into that, but it's something that I've used a couple times now and has sped up Cartesian joins hugely. There's also concepts like windowing and using reduce by key. Slightly running out of time, but one thing here that's important is this concept of you can change very easily by saying repartition, or if you're ever doing something that requires a shuffle, they normally have the number of partitions you can that you can decide to have. At any time in Spark, you can decide how much horsepower you want or don't want in a process, right? So this is an example of if in stage 2 is, let's say it's very CPU intensive, but stage 1 and stage 3 were not, you can repartition it out to say, I want to use more cores, I want to use more memory for this particular stage. And you can make that as variable as you want, depending upon your speed needs, right, and the capacity of your cluster. So, and this is just some results I did with a customer. They had an operation that could only do, a single thread could only do 3,000 records a second, right? It was this big mathematical function. And we just played around with changing the number of partitions. And you can see here, if we went from 1 partition to 32 or 16 partitions, we got, almost, 16 times faster. But from 16 to 32, we didn't get any faster, and that's because we only had 16 cores. But the point of it being, if you have cores, you can continually go faster and faster and faster. Any questions on that? Am I done? I'm done? Okay, I'm done. All right. If you guys have any questions, feel free to get me afterwards. And this slide is really important, but you can go on to, there's a blog post by Sandy Rise about performance optimization of Spark. And this is how memory is divvied up and how you might want to configure it.